Welcome and Namaskaram to Engineering Analytics Laboratories' introductory video series to thermal property analysis. The workhorse of thermal property analysis is the Differential Scanning Calorimeter, or DSC. This introduction course will review the foundational basics of a DSC, show how a DSC operates, provide DSC applications, and outline a few best practices for properly using and maintaining a DSC. Let's take a moment to answer the basic question, what does a DSC do? In short, a DSC measures the heat flow into or out of a sample over a segment of temperature or time. As heat flows into a sample, a thermal transition occurs. In this example, we see a simple step change in the amount of energy flowing into the sample, which represents a thermophysical transformation. Look now at the XY axis of the graph. We see that the heat flow is measured against the temperature and labeled endo up. This is an important distinction for reading this graph and its corresponding data. The step change shown is endothermic, meaning that energy is flowing into the sample from the surroundings in order to initiate the transformation. The tick mark in the middle of the y-axis demarks the boundary between endo and exothermic responses in this graph. Now that we have seen a basic endothermic step change, let's take a look at a more complete picture of a typical polymer response to a thermal cycle, which is heating and cooling. As the sample is heated, first response, second response. Now the sample is cooled and releases heat exothermically, third response, fourth response. This is a complete representative graph of one thermal cycle of a basic polymer. Note that the endothermic and exothermic responses are basically mirrors of each other. This is a generalization, and many will not look so nice. Yet, through this hypothetical generalization, we will make sense of comparing opposite properties such as melting and freezing, or glass transition and crystallization, correct? With this understanding, then, we can understand the basics of what a heat flow graph visually represents. A visual look at the graph always reveals the type of thermal transformations that have taken place. Thinking along those lines, let's look at a few typical thermal graphs. Can you guess the transition before it's revealed? As we saw earlier, this is a glass transition. Looking at the temperature scale, we see a transition over the range of 50 to 200 Celsius. In general, a polymer glass transition appears within this temperature range. The typical data of interest in glass transition is the onset temperature, and for a DSC, the onset temperature is found at the intersection of two tangents off the heat flow curve. The first tangent comes from the base heat flow before the transition begins, roughly. The second tangent is found using the derivative of the heat flow curve. Using these tangents will keep this data consistent among users, equipment, software, and samples. Not using tangents will yield inconsistent data. Furthermore, looking at the curve, see how it's ended higher than when the transition began. This is normal due to the change in thermophysical state and properties of the material. Let's watch another thermal transition and tell me what you think it is. This melt looks visually different from the one shown a few moments ago, right? Melt transitions have their own shape, based on the overall shape, size, and physical characteristics of the sample, but generally they're large and somewhat sharp. Note the temperature scale for this graph. The temperature range is higher than the glass transition range in the graph on the left. Generally, a polymer melt will occur between 200 and 500 Celsius, though this is not a rule, just a generality to help in understanding. Data points of interest for this transition are the onset temperature, the total enthalpy, or area under the curve, and the peak height. Based on the look of a melt, what do you think a freeze transition would look like? The final graph is a cure transition. Did you notice the x-axis now shows time instead of temperature? Cure transitions are often carried out over time at a single temperature, but can also be carried out over a temperature range. Did you notice the difference in the shape of the curve? The cure begins with quick absorption of thermal energy before tapering off as the cross-linking process completes, resulting in a full cure. The total area under the curve and length of time for cure are the primary values sought from a cure transition. We've looked at what a DSC shows us through operation, but what are its operational capabilities? The general operational range of a base model DSC is roughly -30 to 600 Celsius. Adding a liquid nitrogen accessory can get the temperature down to about -140 Celsius. For higher temperature, we have to use a differential thermal analyzer because a DSC's basic design would cause some parts to melt above about 700 Celsius. The DTA's operational accuracy range is roughly between 250 and 1500 degrees Celsius, though this range can vary by manufacturer. And finally, both the DSC and DTA utilize purge gases of either nitrogen or air because nitrogen yields a stable, even, and consistent thermal energy flow. To advance our understanding of a DSC and to properly understand using it, we need to look at the design of a DSC unit. There are two DSC designs, heat flux and power compensated, aka heat flow. The heat flux design was the first to be invented, and the power compensated looks very similar to it. The calculations, though, are different, but that will be explained after we visualize the internal workings of a basic DSC. The first pieces and most important to the function of a DSC are the sample and reference pans. Without the reference pan, no calculation can occur. The reference pan is always empty and of the same style and material as the sample pan. This is exceedingly important to getting correct data. The pans sit on small stands inside a furnace chamber, and the furnace has an outer casing and is insulated to contain as much energy output from the heater as possible. Between the furnace housings and pans is the heating element. A computer controls the amount of energy going into the heater, and this measurement is directly related to the heat flow calculation. Thermocouples are centered directly under the pans. Important note, make sure the pans sit centered on the stands to prevent inconsistent data. An additional thermocouple monitors the furnace temperature for safety and calibration requirements. Finally, a purge gas is passed over the pans to facilitate an even transition of energy around the sides and top of the pan, while also allowing for any off-gassed material to escape before it has a chance to deposit onto the equipment or pan surfaces. The power-compensated DSC has the same basic design as the heat flux, with two primary exceptions. Both pans are contained within separate furnaces, and the heaters are independently controlled. Doesn't seem like such a design alteration would do anything, right? So what does this change mean? A heat flux DSC calculates the energy flow into the sample based on the temperature difference between the reference and sample. The power-compensated DSC calculates the energy flow into the sample based on a fluctuation of energy necessary to keep the sample at the same temperature as the reference. This simple design difference also affects the capabilities of the DSC. A heat flux DSC has greater sensitivity to the subtle changes in a sample, giving it greater precision at detecting small changes. The power-compensated DSC has far greater control over the temperature of the sample and reference cells because the overall volume and mass to be heated are smaller. Therefore, the system can heat and cool a sample more rapidly, yielding certain property tricks that are not capable with a heat flux DSC. Before we get to the importance and timing of calibrating a DSC, let me ask you a question. What temperature does the thermocouple measure? We'll work this out together. Activate the power supply on the DSC and the furnace powers on. As energy is added, the first component to increase its temperature is the heating element. Continue to add energy, and now the thermocouples under the pans begin to increase in temperature. And watch as the system heats. Each component heats in a cascade effect. At this point, every component has begun to increase its temperature, but the heating element is the hottest and the sample is the coldest. Remember that the heat flux DSC does not aim for equal temperatures between the reference and sample pans, but the power-compensated DSC must increase the energy in the sample pan's furnace in order to maintain a sample temperature equal to the reference temperature. More mass, more energy. If in response to the earlier question you answered that a thermocouple measures the temperature at the tip of the thermocouple, you're doing great. The thermocouple will actually be hotter than the sample. Because the thermocouple measures its own temperature and not the sample directly, a DSC must be calibrated. Calibration removes the error caused by the difference in temperature of the thermocouple and sample. It also removes the errors intrinsically caused by the differences in heat capacity and thermal diffusivity rates of the main components of the DSC. The same system errors exist when testing a calibration standard, but the standard has well-known properties in which to compare the measured system data. When all errors are equal, they'll cancel out. Now that we understand the why, let's look at the when. When must we calibrate? Calibrate whenever these operating parameters are changed. Each of these parameters will in some way directly affect either the thermal transition of a material or the equilibrium of the equipment, and that includes the environmental conditions of a room. Finally, recalibrate if a performance verification test fails. We've talked about the what and the how of a DSC, so let's discuss the when do we use it. And we hope this section of the training course will give you boundless ideas of how to use a DSC. Probably the most commonly known use of a DSC is to test polymers, usually for glass transitions and melt points. But really, we like to think that a DSC can be used to answer basic questions like, can I pour this hot coffee in the plastic cup I designed? Such a question is quickly answered looking for the glass transition, but maybe it would also be good to know how much oil remains. Well, that could leach into the hot coffee. A DSC can also help answer that. Metals can also be tested in a DSC. After all, the calibration standards are metals. Simple melts and crystallizations is about the general limit for a DSC, but a few think outside the box researchers are using a DSC to understand how a metal's crystal structure affects inherent thermal properties like heat capacity by quick cooling a metal sample in order to generate alternate crystal structures. Additionally, adhesive curing and thermal cycling effects can be studied. If you designed a new glue meant to adhere a plastic mirror to a car's glass windshield, would you want to know how the thermal cycling of day and night might alter the glass transition temperature of this material between the time the cure initializes and the time the cure completes? Or maybe how many thermal cycles before the material decomposes from thermal stresses on the long chain bonds? Now let's keep our ideas rolling with biomaterials. Many researchers are using DSCs to test human and animal food. Do you want to know when the rice in your Rice Krispies will puff? How much energy does that puff require? Even a novel thermal insulating material was designed around wax encased in cork. The wax absorbs energy from the cork to undergo melt, thus reducing the temperature of the surrounding cork, if only for a moment, allowing the cork to absorb more thermal energy. Finally, quality control for a variety of industries, including the recycling industry. Pick up a plastic bottle. What plastic is this? Put a piece in the DSC to distinguish amongst commonly used plastics based on the melt temperature. Chocolate industry has also gotten in on quality control with DSCs. Chocolate production can generate 2 fatty crystal forms in its finished product. One is desired, one is not, and each has a different melting point. Now that we have looked at the what, how, and when of a DSC, let's wrap up with some basic practices or tips and tricks to get good data and keep your DSC functional. When it comes to your sample pan, the most important aspect is how full and how much surface area is covered. The sample should fill no more than 1/3 of the volume of the sample pan, because large samples cause flawed data due to the nature of heating a larger mass. Also, fill the pan so that as much of the sample's surface area is touching the bottom of the pan, where it's closest to the heater and the thermocouple to get the best results. Now, most sealed pans have a void space just by the nature of the pan. The gas can expand and possibly burst the pan if there's too much sample. But these newer pan styles are coming out that are reducing the void and yielding more accurate data. Once a sample pan is inserted, ensure that a stable heat flow has been achieved before beginning the actual test segment. This usually requires an isotherm for up to 5 minutes to achieve a stable equilibrium. And the final important practice regards the purge gas flow rate. A good and standard flow rate is 20 milliliters per minute. If the rate is too low, energy will sit in the furnace and the sample will heat faster than the system is measuring. Too high, and the energy is not transferring evenly around the pans due to turbulent flow, and those high flow rates can cause the pans to vibrate. And no good data comes from a vibrating pan. Now for a few don'ts. Do not leave the cooling unit running when the DSC is not powered up. This will destroy a $3,000 component. The furnace housings and stands are sensitive to physical forces, so you don't want to clean them with physical force. Just clean the chamber with air at 590 degrees Celsius for about 10 minutes. And do not spill anything into the furnace chamber or its housing. It is sometimes unavoidable, so if something is spilled, program the DSC to run a cleaning cycle and let combustion do its trick. But know that you may have to recalibrate after a spill. We hope you've enjoyed this DSC introductory course and that maybe you've been inspired to test new materials. Please contact us for training on any thermal property testing device, and we'll develop a training course specific to your needs and equipment. Call us right now at area code 321-720-6578 or email us at enganlab@gmail.com. Smarter testing with EA Labs, engineered for your success.